I need to begin with a disclaimer. This is not science fiction. Everything we're going to explore today, solar sails, fusion engines, even antimatter drive research, represents real work being done right now. What excites me is that in 2025 the pieces finally feel like they're connecting in a way they never did before. And when you combine that with James Webb's discoveries of atmospheres on distant exoplanets, we suddenly have a map, an actual list of places we might target. Stay with me, because the updates you're about to see will likely shift how you think about traveling to the stars. The scale of the journey. At first glance, it feels like the stars are right there. You step outside on a dark night, and the sky looks like it's filled with shining neighbors. Many of them are brighter than city lights, some even seem almost within reach. The illusion is powerful. Your eyes are tricked into believing that the universe is small, that perhaps the next star could be just around the corner if we only knew how to get there. But the actual scale of the journey shatters that picture the moment we start to measure it in numbers. By 2025, we can describe those distances with far more precision than ever, and the picture that emerges is staggering. Let's take the closest case. Alpha Centauri is the nearest star system to Earth. When people hear that it's only 4 light-years away, they sometimes imagine that's a manageable figure like driving across 4 towns on a map. Light-years, though, are not ordinary units of distance. They're the measure of how far light itself, the fastest thing we know, can travel in an entire year. 1 light-year is about 6 trillion miles. Multiply that by 4, and Alpha Centauri stands roughly 25 trillion miles away from us. That's not an engineering challenge like building a longer bridge or digging a deeper tunnel. It's a scale that doesn't fit within human experience at all. For comparison, let's shrink things down. The moon is the farthest any human has physically traveled so far. From launch pad to lunar surface, it's about 240,000 miles. Imagine stacking that distance over and over. To equal Alpha Centauri's stretch, you'd need more than 100 million moon trips in a row. Another way to see it is with the orbit of Earth itself. Our planet makes a complete lap around the Sun each year at a distance of 93 million miles. That orbit, if laid out in one line, would need to be repeated more than 270,000 times just to touch the edge of Alpha Centauri's domain. Even if we race the numbers against light speed itself, the story doesn't get much better. A light beam leaving Earth right now would take over 4 years to reach Alpha Centauri. That's the most optimistic timeline the laws of physics allow. For anything heavier than a photon, the challenge becomes overwhelming. The best spacecraft humanity has launched to date, probes like Voyager 1 and Voyager 2, crawl across interstellar space at around 17 kilometers per second. They've already spent decades moving at that pace, yet even at their remarkable velocity, Voyager would require more than 70,000 years to get to the nearest star. That's not an academic statistic. It's the raw time it would take inside the spacecraft clock. Think about how long 70,000 years really is. Entire civilizations rise and fall in less than 5,000 years. Written history covers only about 6% of that span. If one of those probes had left during the Ice Age, when mammoths still roamed Earth, it would only now be less than 1% of the way to Alpha Centauri. That's why every engineer and scientist working on interstellar concepts insists on starting the conversation with scale. If you don't first understand the raw enormity of the problem, every propulsion breakthrough sounds trivial, every cost comparison feels manageable. But once you lay out the raw math, you see why current methods can never get us there. There's also the psychological side of distance. Human minds adapt to measured space in relative ways. A person hears about a commercial flight of 12 hours and accepts it as long, but still tolerable. The same with a drive across multiple states, or even the months it took astronauts during the Apollo program to plan lunar journeys. All of those experiences give us a sense of confidence that long trips are possible if you organize resources correctly. But a star voyage cuts completely outside of that framework. It's no longer about long weekends or drawn-out expeditions. It's about time spans that far outstrip a human life, many times over. This difficulty is part of why science fiction stories often leap directly over the distance problem. They imagine ways of changing space itself, wrapping, folding, or leaping through dimensions. Those are narrative shortcuts, because in practical terms, traveling to another star is the slowest road humanity has ever imagined. If you scaled the Earth-Moon distance to the length of a single step, Alpha Centauri would be about the length of a daily marathon away. You'd be running all day, every day, carrying that step over and over again just to glimpse the nearest system. And that is only the first stop in a galaxy with hundreds of billions of stars. Now think about the resources tied to such journeys. Every rocket we launch today measures fuel in tons, payload in kilograms, and budgets in the billions. But when confronted with 25 trillion miles, numbers of that scale immediately collapse. You could launch rockets every year without pause, and they would barely move humanity toward the finish line. The curve of progress flattens into impossibility, which is why the question isn't about commitment or patience. It's about whether our technology can close the enormous gap between human ambition and astronomical reality. That's why Alpha Centauri remains a symbolic benchmark. It's not only the nearest known neighbor, but also the system with a confirmed exoplanet, Proxima b, orbiting within the habitable zone. It represents the shortest possible interstellar challenge, the easiest trip humanity might someday attempt. Yet, despite being the least distant target, it is still so far away that existing technology is essentially irrelevant for the job. Talking about Alpha Centauri forces us to confront just how unprepared conventional engineering is for this journey. By 2025, astrophysicists and mission planners have become increasingly blunt on this matter. Distances this vast cannot be overcome with gradual improvements in our current launch designs. You cannot stretch the lifetimes of satellites by another decade and expect it to matter. You cannot extend a mission budget slightly and expect meaningful progress. There has to be a fundamentally different way to cross space, one that works with the distances at hand rather than struggling against them. Grasping the scale of the journey does more than set the boundaries. It also acts as a guidepost for innovation. When engineers build propulsion concepts today, they know they are competing against hard numbers like 70,000 years by chemical rockets versus at least 4 years as a light speed minimum. Somewhere between those two limits must lie the technologies of the future, technologies that can shave tens of thousands of years down to centuries or even decades. The understanding of scale makes that search focused rather than blind. So while it's tempting to look at the night sky and feel that the stars are close, the 2025 reality shows us they are not even on the same map as human travel so far. Every mission we've flown to the Moon, to Mars, to the outer planets, has been a local errand in cosmic terms. The stars remain whole continents away, and all of our most trusted methods of travel leave us stranded at the starting line. That is exactly why the next step isn't about launching faster rockets of the type we already know. It's about venturing into propulsion methods that can actually challenge the scale of the universe itself. The limitations of chemical rockets. When we think about humanity's journey into space, rockets are always at the center of the picture. They are the engines that carried astronauts to the Moon, delivered rovers to Mars, and launched satellites that now shape everyday life on Earth. Without chemical rockets, space exploration would never have left the drawing board. They provide the immense thrust needed to overcome Earth's gravity, and for that role they stand unmatched. Every milestone we celebrate, from Apollo missions to the International Space Station, happened because we had these workhorses. But the bigger question is, can the rockets we know today reach beyond planets and into the realm of stars? Could the same technology that launched us across the solar system extend to another star system? Intuition might say yes, since rockets already cross hundreds of millions of miles. The truth, however, is that the physics behind chemical rockets places hard barriers that cannot be stretched to interstellar scales. The limitation is not a matter of effort, funding, or improvements in building techniques. It comes down to an equation first described in the early 20th century, known simply as the rocket equation. It is one of those deceptively simple relationships that is easy to write, but impossible to escape. The basic idea is straightforward. The faster you want a rocket to go, the more fuel you must carry. But that additional fuel adds weight, which requires even more fuel to accelerate, which in turn adds more mass, and the cycle quickly spirals out of control. It creates an exponential wall where trying to squeeze out more speed becomes impractical. Every engineer evaluating chemical propulsion eventually meets this same wall. It explains why we can launch to the moon, why we can cross to Mars, but also why a star mission under the same rules would fail. One way we measure the efficiency of any rocket system is through its specific impulse, called ISP. This value tells us how effectively a rocket turns fuel into thrust. For most chemical rockets, the ISP sits in the range of about 300 to 400 seconds. Even the very best examples fall into that same narrow zone, which is already near what the chemistry of propellants can allow. This means that the rockets we fly are not flawed designs waiting for better engineering. They are already operating close to physical limits set by chemistry itself. As one NASA scientist framed it, chemical rockets are about as efficient as physics will allow them to be. That point is crucial because it eliminates the idea that minor advances will unlock dramatic new performance. Chemical propulsion cannot be stretched all the way to the stars. To see why, let's scale the number. If you imagine a standard chemical rocket aiming toward Alpha Centauri, the nearest star system, the travel time is staggering. With an ISP of around 400 seconds, the math gives us a journey that would last roughly 50,000 years. That's 5 times longer than all of recorded human history. It is longer than the existence of many species on Earth. So even in the most generous scenario, such a trip collapses under its own timeline. Unlike a trip to Mars, where months of travel line up with human mission planning, a voyage of that length is meaningless to us as a species. No spacecraft can be maintained that long, no society can plan over such time spans. It stands outside the range of practical engineering. We can also look at real examples. The Voyager probes, built and launched in the late 1970s, are the fastest chemical rocket-based objects we have sent out of the solar system. They are now on true interstellar paths, leaving the influence of the sun. Yet even at their extraordinary speed, if pointed squarely at Alpha Centauri, they would require more than 70,000 years to arrive. When they eventually lose power, as they will in just a few years, their journey will continue in silence across the galaxy. A journey with no destination because of the overwhelming timescale. If Voyager does illustrate anything, it is that chemical propulsion can launch probes beyond planets, but not with any meaningful hope of closing the distance to stars. From the perspective of 2025, space agencies understand this with clarity. Rockets remain absolutely indispensable for leaving Earth itself and reaching orbit. No other technology can yet provide a concentrated burst of thrust like a chemical rocket, and that capability is non-negotiable for lifting spacecraft away from the surface. But once in space, their usefulness diminishes rapidly if the goal is interstellar travel. Agencies like NASA now treat rockets as the opening stage of a journey, not the complete system. They form the base, but they no longer represent the dream of carrying us across the stars. This distinction matters because it shapes where research dollars go. If chemical rockets could be re-engineered to gain orders of magnitude in efficiency, the problem would look very different. But by now it is widely accepted that chemistry has done nearly all it can. No matter how carefully refined the design, at some point the rocket equation tightens its grip. Instead, investments must move into propulsion methods that abandon chemistry entirely. This shift has already happened in planning documents and mission concepts. The stars require methods that bypass the exponential trap and scale with distance more effectively, whether through fusion, solar sails, or other exotic ideas still at the conceptual stage. There is also an important psychological angle to this truth. Since rockets took us to the moon, they inspire a natural confidence. If they achieve that leap, why not the next? But here the numbers resist optimism. You cannot simply scale the Apollo method to a larger target. The space between Earth and Moon looks vast to us, but against the measurement of light years, it is a fraction with no meaning. Believing that rockets will evolve into starships misunderstands the physics that underpins them. The laws of motion do not give ground to persistence alone. They need new ideas entirely. Some proposals try to bend the role of rockets back into interstellar concepts. They imagine colossal vehicles stockpiled with immense quantities of propellant, launched in stages or reassembled in orbit. But each of these ideas dissolves into mass ratios that collapse the mission before it begins. A ship that carries enough fuel to cross even a modest fraction of a light year would be so massive that no launch system could ever lift it, even with hypothetical global cooperation. The rocket equation does not leave room for a clever trick. It is absolute. So where does this leave rockets in the interstellar question? Essential, yes, but for a role limited to the start. They will always provide the brute force necessary to punch through the thick air of Earth's atmosphere, carrying payloads up to orbit where new propulsion methods can take over. Beyond that, though, they are not the engine that will ever take us to another star. Rockets are powerful tools, but for moving between stars, they cease to matter. And understanding why gives us a clear boundary. Every plan for reaching Alpha Centauri and beyond must leave chemical propulsion behind at the very first step. Fusion propulsion, harnessing the power of stars. For decades, humanity has been trying to answer the same question. Can we harness the same reaction that powers the sun and turn it into a propulsion system? Fusion has always been at the center of that dream. The process itself is well understood. Two light atomic nuclei collide at extreme temperatures and pressures, and in merging, they create a heavier nucleus, releasing energy. It is nature's ultimate power source. We already know this firsthand because it's happening continuously in the heart of our sun, producing the light and heat that makes life possible here. What makes the concept so attractive is its efficiency. When compared to chemical reactions, fusion releases millions of times more energy per unit of mass. That alone explains why it captures the imagination of space scientists. If you could ever package fusion into a rocket engine, interstellar distances suddenly become far less overwhelming. The tension is that while we can make fusion happen for split seconds in massive laboratory settings, we are nowhere near shrinking it into a compact, reliable, controlled form suitable for a spacecraft. Recent years have added new momentum to this field. In December 2022, researchers confirmed that for the first time a controlled fusion reaction produced more energy than was required to ignite it. That milestone, often called net gain, was achieved in the National Ignition Facility using powerful lasers to compress fuel pellets. By the standards of Earth-based laboratories, it was a narrow success. Net energy in, net energy out. But symbolically it crossed a barrier that had stood for over half a century. Instead of saying someday we will achieve this, we can now say we have achieved it, at least in controlled experiments. Between 2022 and 2024, further repeat demonstrations confirmed the effect under different conditions, showing that the principle wasn't just a one-time fluke. For spaceflight, those milestones don't mean we are ready to load fusion drives into rockets, but they signal a turning point. The basic physics is sound. The task left is engineering, and that path brings a very different set of struggles. To understand why this matters to propulsion concepts, think about what happens if you take that kind of reaction and redirect its energy into thrust. The most famous conceptual studies were Project Daedalus in the 1970s, and later, Project Icarus as a follow-up in the early 2000s. These were detailed design efforts led by teams of engineers and scientists, not science fiction writers. They sketched out spacecraft measured in kilometers, equipped with huge fusion chambers that would ignite tiny pellets of deuterium and helium-3. Each miniature burst of fusion energy would generate plasma, expelled through magnetic nozzles, pushing the vessel forward. In calculations, such ships could reach perhaps 10 to 15% of light speed. Suddenly, a 70,000-year trip to Alpha Centauri shrinks to under a century. In human terms, that is still enormous, but it is also a timescale that can be organized. A multi-generation voyage becomes imaginable. Today, in 2025, those designs remain on paper, but their legacy drives new studies. Various agencies have returned to fusion as one of the few propulsion modes that could actually cross interstellar spans. Fusion is compact compared to beamed energy sails or nuclear bombs exploding behind a plate. It has the elegance of using energy-dense reactions, governed by known physics, with a clear potential performance margin. The timeline, however, is a sobering one. Even optimists only suggest that laboratory-scale fusion drives may appear for deep space probes by mid-century. Some conceptual roadmaps tentatively draw the 2050s as a period when fusion-driven probes, without humans aboard, might actually leave the solar system at meaningful fractions of light speed. But here's the obstacle side. Every advance in fusion highlights the sheer size of the machinery required. On Earth, the test beds that enable net-gain fusion fill entire buildings. They require enormous magnetic fields from superconducting coils, cryogenic systems, and massive laser arrays. None of those things are remotely portable today. If you look at a diagram of ITER, the International Fusion Reactor under construction in France, you realize the scale. It is the size of a power station, with thousands of tons of hardware. How do you shrink something like that into a Starship engine? It isn't just miniaturization. It's about maintaining extreme conditions. Temperatures hotter than the sun's core, pressures that only advanced magnetic confinement can hold, and precise timing to ignite fuel pellets rapidly. Translating that into a system that can operate in space without constant technician maintenance is a challenge unlike anything we've faced. Weight adds another serious dimension. For spacecraft, mass is the ultimate currency. Even if fusion fuel such as deuterium is compact, the containment systems are heavy. Every ton of infrastructure launched from Earth multiplies costs and complexity. Engineers sometimes speculate about building such vessels entirely in orbit, using materials ferried aloft in segments, or even harvesting fuel from lunar deposits rich in helium-3. Those ideas are not physically impossible, but they stretch well beyond current capability. It means that even if fusion physics is solved perfectly, the engineering translation could still take decades more. You are not only asking, can we ignite the reaction? But also, can the ignition chamber survive tens of thousands of continuous bursts without failing? In actual spacecraft engineering, durability stands as high a hurdle as ignition. Despite this realism, fusion remains at the forefront of propulsion studies for one reason. There is no credible substitute. Solar sails accelerate too slowly for crewed missions. Antimatter, while hypothetically perfect, cannot be produced in the required amounts. Nuclear fission, although powerful, lacks the thrust-to-specific impulse ratio sufficient for true interstellar leaps. Fusion balances feasibility with performance. It is not easy, but it is possible within the laws of physics and does not require exotic materials that we cannot yet imagine. That kind of credibility matters as agencies and think tanks map future starbound probes. An example shows this balance. Imagine a probe launched in the 2050s using what some designers call an inertial confinement drive. It would carry thousands of tiny fusion pellets, each ignited many times per second by advanced lasers or magnetic pulses. The expelled plasma would drive exhaust velocities measuring in tens of thousands of kilometers per second. At a fraction of light speed, such a probe could plausibly reach nearby stars within a human lifetime. To keep the system stable, it would require automated repair systems, magnetic fields stronger than anything today's spacecraft carry, and continuous onboard power just to keep the confinement systems running. No one has built such a machine, but no one has proven it is impossible. That is the difference separating it from pure speculation. It helps to imagine the moment when a small test platform, perhaps not much larger than a car, demonstrates a sustained fusion pulse drive in orbit. That demonstration will be the milestone everyone watches for. Right now, fusion propulsion is a sequence of models and laboratory physics. By the mid-21st century, if progress holds, that line may finally be crossed. In that sense, fusion propulsion has advanced beyond fiction. It is no longer a poetic dream of bottling a star. It is a rigorous engineering pathway, lined with known problems that have possible solutions. The dates are long, stretching into the second half of this century, but the direction is no longer vague. For the first time, interstellar propulsion by fusion is seen as a roadmap drawn in pencil, ready to be inked when the supporting technologies fall into place. Solar sails riding the sun. Imagine standing at the edge of the ocean with a sailboat. The boat doesn't carry barrels of fuel and it doesn't need an engine. It simply raises its sail, catches the wind, and begins to glide across the water. Now replace the ocean with the vacuum of space, and instead of air pushing a canvas, it's light itself pressing against vast reflective sheets. This is the idea of solar sailing, traveling without fuel, moved only by sunlight. It sounds counterintuitive because sunlight feels weightless on our skin. But in physical terms, photons carry momentum. When they bounce off a shiny surface, they impart a tiny push. The push is small, but it never stops as long as the sail faces the source. Over days, weeks, and months, those pushes accumulate into steady acceleration. A spacecraft propelled this way could begin its journey more slowly than a rocket, but unlike rockets, it wouldn't need to burn a single drop of propellant to continue gaining speed. The first time humanity demonstrated this in space was in 2010 with Japan's IKAROS mission. That spacecraft used a sail measuring around 200 square meters, coated with thin-film solar cells to collect power. Though small by the standards of interstellar concepts, it was enough to prove that sunlight could be harnessed to change a spacecraft's trajectory. IKAROS is remembered not just for sustaining solar sailing, but also for showing that steering is possible. By shifting the reflectivity of different sail sections, engineers could control its angle relative to the sun. In practical terms, the mission was modest. It flew past Venus and gathered data on its sail dynamics. Yet in historical context, it was the first step toward a kind of propulsion that requires no fuel tanks, no engines, and no worry about running out of propellant on a multi-year voyage. NASA soon joined the effort, testing progressively larger systems. The Near-Earth Asteroid Scout, a CubeSat mission launched with the Artemis I flight, carried a sail measuring 86 square meters. Unlike IKAROS, NEA Scout was a compact package, showing that solar sails could fit into the architecture of lower-cost missions. Though its deployment faced technical challenges, the very fact that NASA placed a solar sail on a lunar flight underscored growing confidence in the method. In parallel, another NASA-led experiment called the Advanced Composite Solar Sail System, or ACS-3, focused on the materials problem. A solar sail is only as effective as the booms that keep it stretched open, and traditional metal structures can be heavy. The ACS-3 project tested composite booms, lightweight yet sturdy, that could hold larger sails taut without collapsing under dynamic forces. Designed from a CubeSat, ACS-3's sail stretched nearly the size of a small apartment, about 9 meters per side. It may not impress when compared to a football field, but it marked the start of scalable designs. Engineers now picture sails expanded to hundreds, even thousands of square meters. Looking forward, NASA's solar cruiser, expected to fly mid-2020s, is on track to be the largest solar sail spacecraft so far. With an area of about 1,600 square meters, it represents a leap in magnitude compared to earlier missions. That's a surface larger than 4 tennis courts placed side by side. The reason for scaling up is simple. The more surface area available, the more photons can strike and push. For a small sail in low Earth orbit, photon pressure is barely detectable compared to atmospheric drag. For a kilometer-scale sail in deep space, the effect is continuous and measurable. Solar Cruiser is designed not just to prove deployment works on an unprecedented scale, but also to test maneuvering capabilities that practical missions would require for navigation near planetary bodies. In this sense, Solar Cruiser is not an academic experiment. It's a stepping stone toward operational solar sailcraft that could fly real missions. The strength of solar sails lies in their endurance. Chemical rockets burn heavily at the start, then coast with no further acceleration. A sail, by contrast, provides low thrust endlessly, as long as photons are available. At first, the acceleration feels imperceptible, fractions of a millimeter per second squared. But leave the sail exposed long enough and the numbers add up. After several years of uninterrupted sunlight, speeds in the tens or even hundreds of kilometers per second become feasible for lightweight craft. While that still falls far short of fractions of light speed, it opens real possibilities for crossing the solar system. Missions to the outer planets or to interstellar space suddenly have an engine that never runs out, provided the sail remains intact and oriented. In engineering discussions, this is often described as propellant-free propulsion, an advantage that no other method can currently match. But sunlight alone will not push sails fast enough to meet interstellar goals. The ultimate vision is to take the same reflective sheets and hit them not only with natural sunlight, but also with directed beams from lasers or even microwave transmitters on Earth or positioned in orbit. The physics does not change. Photons still transfer momentum, but with lasers, the intensity can be orders of magnitude stronger than sunlight. Scale the sail to kilometers in size, fire a laser array for a short period, and the acceleration grows dramatically. In concepts like these, microscale probes weighing only grams could be pushed to a significant fraction of light speed within minutes or hours of illumination. That is the heart of Breakthrough Starshot's plan, a privately funded initiative to send tiny probes to the Alpha Centauri system. Solar sails powered by Earth-based laser arrays represent perhaps the clearest pathway towards a practical interstellar mission that could operate within decades rather than centuries. There are obstacles, of course. Building kilometer-scale sails is a materials challenge. The films must be thinner than a human hair yet strong enough to endure micrometeoroid impacts. Deploying sheets of this size in space must be flawless, because even a minor tear or tangle could ruin the entire mission. Steering such a platform under intense laser bombardment adds further complexity. It must remain stable under forces millions of times larger than from sunlight alone. And then there is the infrastructure. Constructing a ground-based laser array powerful enough to launch probes across interstellar distances would likely demand tens of gigawatts of energy, requiring political and financial cooperation on a scale not yet seen in spaceflight efforts. Still, none of these barriers appear insurmountable in theoretical terms. They are expensive and complicated, not impossible. It is also important to recognize that smaller sails, without lasers, already provide operational benefits. Missions targeting near-Earth asteroids or orbit adjustments within the solar system do not need high fractions of light speed. For them, the ability to maneuver without fuel is transformative. Imagine a sailcraft slowly spiraling inward toward the sun, adjusting trajectories over years without propulsion tanks or engine failures. Such vessels could monitor near-sun regions, study solar physics, or act as scouts for planetary defense. These kinds of duties justify smaller, nearer-term sails long before the dream of star travel is attempted. By 2025, solar sailing has shifted from concept papers to flying missions, Agency demonstrations have proven that sails can deploy, maneuver, and sustain themselves in real environments. The next step, already underway, is scaling up to meaningful areas capable of accelerating probes beyond the reach of planets. This gradual climb does something important. It builds credibility. Instead of being a science fiction prop, a solar sail is now a flying, functioning spacecraft choice. When combined with the idea of external lasers, it transitions from interplanetary tool to an interstellar prospect. For people asking when humanity will first touch another star, solar sailing offers one of the few available answers that feels like a roadmap rather than a wish. It may still require decades to reach its full scale, but unlike many propulsion dreams, it is already underway. Project Orion and nuclear pulse concepts. Could nuclear explosions themselves ever become the engine of a starship? It sounds almost like a thought experiment designed to shock. Yet in the late 1950s, this was not only proposed, but it became the centerpiece of a funded project. Known as Project Orion, it attempted to take one of humanity's most destructive technologies and transform it into a propulsion method powerful enough to leap well beyond the planets. Unlike chemical rockets, which burn fuel continuously, Orion's strategy was radically different. The concept was to carry a giant, armored pusher plate at the back of the spacecraft. Small nuclear devices would be ejected behind it, detonated at timed intervals, and each explosion would hit the plate with a blast. Shock absorbers attached to the plate would then transfer the momentum in controlled pulses, pushing the enormous spacecraft forward. In theory, it was a way to turn terrifying blasts into precise acceleration. At the time, the project drew interest for both civilian exploration and military potential. The United States Department of Defense had an eye on it because of the Cold War. If you could launch giant vehicles into space without regard for fuel weight limits, you could gain not just scientific reach, but strategic advantage. The project's design team even constructed test rigs to prove the principle. Non-nuclear explosives were detonated beneath steel plates affixed to small models, and motion was captured on high-speed film. The results confirmed that a series of pulse detonations could indeed drive a craft forward without destroying it. For the researchers, it was a moment of validation. The idea was not only clever in theory but workable in demonstrations. Project Orion's originators understood its scope. Among them was Freeman Dyson, who analyzed and promoted the concept. At meetings, Dyson explained that Orion could reach astonishing speeds. Calculations showed that with enough detonations, an Orion-style vehicle might achieve around 5% of the speed of light before leaving the solar system. That figure is striking. 5% of light speed collapses interstellar distances that chemical rockets stretch into tens of thousands of years. Instead of a voyage lost across millennia, you could imagine a journey measured in centuries or even less. In purely physical terms, Orion had the potential to become a genuine interstellar propulsion system. But almost from the moment it began, Orion was shadowed by practical and political barriers. Each nuclear detonation, if performed near Earth, would scatter fallout through the atmosphere. This was not a small side effect. The number of explosions required to launch a full Orion spacecraft into orbit numbered in the hundreds or thousands. Even small nuclear devices are catastrophic in terms of radiation. Detonating them in Earth's atmosphere would not only undermine environmental safety, but also devastate global health for generations. It was quickly recognized that a ground-to-orbit application was especially unworkable. International treaties barring nuclear tests in the atmosphere only made the point more explicit. Even if one imagines assembling such a craft in orbit and detonating pulses only in the emptiness of space, the political challenges remain severe. International agreements treat the deployment of nuclear explosives in space as unacceptable. From a military perspective, it amounts to placing nuclear arsenals in orbit, a trigger for global suspicion and potential conflict. From an environmental perspective, the danger of an accident during launch, Imagine a rocket carrying hundreds of nuclear devices breaking apart on ascent. Remains a nightmare scenario. The very feature that gave Orion its potential was the same factor that chained it in impossibility. Nuclear weapons are not just tools. They carry ethical weight, symbolic and literal fallout that places them outside the reach of engineering optimism. Still, the concept itself never entirely faded. Engineers often point out that Orion worked on paper. Its physics required no exotic matter, no hypothetical breakthroughs, and no particles beyond the standard model. Compared to speculative propulsion systems, Orion is remarkably straightforward. In that sense, its tragedy lies in practicality. It could work, but it likely never will. Some have asked whether it could be reborn under different circumstances. If humanity eventually builds large-scale infrastructure in orbit or on the moon, might Orion be revisited as a way to send freight or giant vessels across interstellar gulfs? If nuclear devices were developed for this purpose and never handled on Earth, could the environmental risks be significantly reduced? These questions arise at conferences and in aerospace literature, though usually posed as hypotheticals rather than roadmaps. What complicates any rebirth scenario is that nuclear handling itself is tightly bound to treaties. For decades, nations have worked to limit proliferation, forbidding the placement of nuclear weapons in orbit or the testing of such devices in outer space. Project Orion's design does not distinguish between peaceful propulsion and weapons capability. The same stockpile of nuclear devices designed to accelerate a spacecraft looks indistinguishable from a military arsenal. Politically, that is not a feature you can separate. Any attempt to build such a system would break open agreements fundamental to international stability. It becomes clear why the project closed in the early 1960s and has remained closed ever since. From an engineering standpoint, the materials problem is also daunting. The pusher plate itself would need to endure thousands of repeated nuclear blasts. Although calculations suggested it was possible with specially coated steel and oil buffering systems, the fatigue on such components across decades raises deep questions of durability. The shock absorbers, meant to smooth each pulse into a manageable push, would be put through stresses unlike any known machine. Even if we set aside politics and ethics, the mechanical survival of the craft still sits at the edge of credibility. If there is any continued relevance of Orion, it is in reminding researchers what is technically possible with present-day physics. At 5% of light speed, a pace Orion might reach, human expeditions to nearby stars could take place over hundreds of years instead of tens of thousands. That difference is staggering. It demonstrates that nuclear pulse concepts opened a door that was closed by chemical rockets. It is why Orion is still a figure in textbooks and propulsion discussions. For every impractical layer of politics, its core mathematics remains sound. In circles considering the very long-range future, some have suggested Orion-like concepts might return in modified forms. Instead of fission-based devices, fusion microexplosions could be used, reducing some of the environmental concerns. Assembling a vehicle entirely off-world, potentially on asteroids, might dodge the most dangerous phases of launch. None of these suggestions change the central problem. The propulsion requires detonations of nuclear-class energy again and again, in a political context where even one detonation is globally unacceptable. Until the cultural, legal, and ethical framework changes, which seems unlikely, Orion will remain a plan frozen in history. The lesson is sobering yet instructive. In propulsion studies, not all working concepts are viable. Some fail on physics grounds, others on cost, and some fail because the side effects outweigh the benefits. Project Orion sits firmly in the third category. It was an idea translated rigorously into numbers, tested at scale with non-nuclear charges, and championed by respected physicists who believed in its core design. By those measures, it succeeded. But against the backdrop of fallout, radioactive risk, treaties, and the symbolism of nuclear weapons, it had no chance to survive. The stars may one day be reached by sails, fusion reactors, or engines we have not yet invented. Nuclear pulse propulsion, however, is likely to remain what it has been since the 1960s, a model sitting in archives, a reminder that technological feasibility alone does not guarantee a path forward. Antimatter, the ultimate propulsion battery. If you've ever watched science fiction, you've likely seen antimatter drives imagined as sleek, glowing engines able to hurl ships across the galaxy. What makes this different from some of the more fanciful technologies is that antimatter is not fiction. Physicists actually create it every day inside particle accelerators. The amounts are microscopic, single particles or small clouds suspended for fractions of a second. But it is real matter, just with reversed electric charge. For example, the antimatter partner of the electron is called the positron, identical in mass but carrying a positive charge. When matter and antimatter meet, the result is annihilation. Their mass converts entirely into energy. Unlike chemical reactions, which release only a small fraction of the energy bound in atoms, or even fusion, which still has limits, matter-antimatter annihilation produces near-perfect efficiency. That is the appeal. If one could ever harness significant quantities, a gram of antimatter reacting with a gram of normal matter would release energy on the order of tens of thousands of tons of TNT. For spacecraft, the promise is straightforward. No other fuel source packs more energy into less mass. It helps to look at this in terms of specific impulse, the yardstick used to compare propulsion systems. Chemical rockets offer a few hundred seconds of specific impulse. Nuclear thermal rockets might rise into the low thousands. Fusion concepts can theoretically exceed 10,000. Antimatter lies far beyond all of them, with calculated values in the millions. In other words, a spacecraft powered by antimatter could accelerate for long periods and reach substantial fractions of the speed of light, while carrying only a small amount of reaction mass. Unlike fusion, which requires massive reactors, antimatter annihilation needs only containment and a supply of conventional propellant to channel the energy for thrust. As a principle, it is the ultimate propulsion battery. The roadblock becomes clear the moment we ask whether we actually have enough antimatter to even test this. By 2025, global facilities such as CERN and Fermilab produce antimatter in minute amounts for scientific study. Positrons are created in radioisotope decay, and antiprotons are generated in high-energy collisions inside accelerators. But to put minute in perspective, all of human production over decades adds up to nanograms. A nanogram of antimatter could, in theory, power enormous explosions, yet harnessing it for propulsion requires at least grams. The difference between what we can generate today and what we would require is not a matter of scaling production slightly. It is a gap of billions in quantity. The cost of producing even a fraction of a gram is estimated in trillions of dollars. Unless methods improve by unthinkable orders of magnitude, antimatter propulsion remains symbolic rather than tangible. Storage poses an equally severe obstacle. You cannot keep antimatter in a simple container. Touching the walls would annihilate it instantly. This means confinement demands sophisticated magnetic or electric traps that suspend the particles without contact. In laboratory experiments, penning traps and similar devices manage to hold small amounts of positrons or antiprotons for seconds or minutes at best. Scaling that into storage for spacecraft means designing magnetic fields strong enough to isolate macroscopic amounts for years, all within practical mass limits. Even the vacuum inside our best space systems still carries stray particles. Any collision with antimatter would release catastrophic energy. The challenge is more than technical, it is existential for the hardware. A leak measured in micrograms could destroy the craft outright. Despite the massive barriers, students and researchers often explore theoretical designs using antimatter. One common approach is called the antimatter-initiated microfusion drive. Instead of using antimatter annihilation directly to produce thrust, tiny pellets of fusion fuel would be ignited by injecting antiprotons. The annihilation triggers conditions for fusion, releasing large amounts of energy with far less antimatter than would otherwise be required. In principle, this combines the efficiency of antimatter with the more manageable physics of fusion reactions. Such designs could reduce the amount of antimatter needed by several orders of magnitude, lowering the demand from grams to perhaps milligrams. Still far beyond present capability, but at least within a discussion that engineers can map onto space missions. There are also spacecraft studies proposing beam-driven antimatter usage. In these models, antimatter would not even be stored in bulk on board. Instead, it might be produced elsewhere, perhaps in orbiting facilities or on moons, and then beamed to an engine at the time of use. This idea skirts the storage issue but raises a different problem: creating the infrastructure. Beaming vacuum-separated antimatter safely across even short distances pushes beyond what 2025 technologies can achieve. Yet the act of designing these concepts suggests the intensity of interest. Engineers and physicists continue to test the boundaries, not because propulsion is anywhere close, but because the rewards are unmatched. The fascination with antimatter also lies in its symmetry with matter itself. In theory, the universe should contain as much antimatter as matter, yet for reasons still not fully explained, matter dominates. That fact leaves antimatter both a puzzle in cosmology and a promise in technology. Each laboratory experiment that captures a few antihydrogen atoms is not only probing cosmological asymmetries, it is also inching toward a better understanding of how antimatter behaves under gravity and under confinement. For propulsion design, these are not trivial issues. If antiparticles can be guided and stored more reliably, the leap from microphysics to engineering prototypes becomes less abstract. At present, antimatter propulsion rests in a paradoxical place. On the one hand, it offers the clearest route to fast interstellar travel. With annihilation efficiencies measured in the millions, a ship carrying just a few kilograms could, in theory, attain a significant fraction of light speed. That would shrink Alpha Centauri missions from tens of thousands of years down to mere decades. On the other hand, every practical step, production, storage, safety, remains insurmountable given today's resources. Funding agencies acknowledge its potential, but they rarely place it in near-term roadmaps. Too expensive, too difficult, too far removed from current engineering. The dream rests both on firm scientific footing and on a mountain of missing infrastructure. The state of the field in 2025 is that antimatter is a laboratory subject, produced atom by atom, studied for physics rather than propelled spacecraft. Some researchers continue to refine storage traps with superconducting magnets, trying to extend confinement times. Others look at decay patterns of isotopes that release positrons naturally, asking whether practical harvesting could ever emerge. No current pathway suggests a useful supply arriving soon. But because antimatter lies inside known physics, unlike many speculative warp drive ideas, it persists as a serious candidate on the long-term horizon. When future generations scan propulsion concepts, antimatter is always placed near the far end of possibility, theoretically unbeatable, yet hopelessly out of reach for now. For those considering humanity's interstellar future, antimatter serves as a kind of horizon line. It tethers imagination to the extremes of physics while reminding us how much engineering remains undone. Chemical rockets cannot inch toward it. Fusion offers nearer-term promise. Solar sails put craft in flight today. But in the race for ultimate velocity, nothing compares in principle to antimatter. Whether it becomes a real propulsion battery or remains forever confined to particle labs, it highlights the spectrum of solutions, from what is practical today to what is possible only under ideal conditions. The dream of an antimatter engine is not about whether physics allows it, it does, but whether humanity can ever build the tools to tame it. The breakthrough Starshot vision. In the conversation about how we might actually send something to another star, most ideas land firmly in the zone of theoretical diagrams or far-future speculation. Breakthrough Starshot is different. It is not an academic exercise or a faint vision based on exotic, undiscovered physics. It is a privately funded, international program that has already gathered teams of scientists and engineers with a single stated goal: send tiny, gram-scale probes to Proxima Centauri in the coming decades. To understand the weight of this, it is important to note that Proxima Centauri is not an arbitrary choice. It is the closest star to us, and around it orbits an exoplanet called Proxima b, which sits inside its habitable zone. For the first time in history, we have a target star and a specific world circling it that might host the right conditions for liquid water. That clarity pushes breakthrough Starshot from vague ambition into purposeful design. The method proposed is laser-driven sails. On its surface, the sail looks like the thin reflective film discussed earlier in solar sailing, but scaled to an extreme. Instead of relying on the sun's diffuse photon pressure, Starshot proposes using a powerful ground-based laser array to focus immense beams onto these delicate sheets. The photons, traveling at light speed, collide with the sail and transfer momentum. Unlike rockets, no fuel is carried on board. Unlike sunlight, the power is concentrated and controlled from Earth. By directing a focused beam for minutes rather than years, a sail weighing just a few grams could be pushed to extraordinary velocities. The target speed is about 20% of light speed. At that pace, the probes could cross the 4.2 light-year gap to Proxima Centauri in just over 2 decades. That figure alone changes the question. Instead of waiting millennia, the travel time becomes a single human generation. The key lies in the infrastructure. The proposed laser array is not a single device, but a coordinated field of thousands of smaller lasers working in combination. When synchronized, they generate a coherent beam of immense power, sufficient to strike a sail thousands of kilometers away in space. The sail itself must be engineered to withstand both the force of the photons and the heat that would otherwise tear it apart. Materials discussions here become critical. The films must be ultra-thin to keep the craft lightweight, but also highly reflective to minimize absorption. Traditional metals would simply vaporize under such concentrated beams. Research in advanced dielectrics, nanostructures, and photonic crystals is underway to identify films capable of surviving illumination at levels millions of times stronger than sunlight. This is already a material science challenge quite unlike anything addressed before, and it explains why Starshot cannot be attempted with off-the-shelf designs. By 2025, updates on Starshot's progress show that while the full-scale laser system is far from realization, important prototyping steps have taken place. Small-scale test sails have been fabricated in laboratory conditions, demonstrating key reflective properties. Experiments using high-powered laboratory lasers have examined how these ultra-thin sheets respond to rapid heating and how their structure deforms under energy influx. On the electronic side, designs for the star chip, the integrated circuit that would serve as the probe's payload, have been drafted down to gram-mass scales. These chips aim to carry not just communication hardware, but also cameras, sensors, and star trackers. The vision is that each probe becomes an independent spacecraft the size of a postage stamp, carried across interstellar space on the back of its sail. With mass this low, acceleration to relativistic velocities becomes feasible without needing prohibitive energy from the ground-based lasers. Funding updates in 2025 clarify the seriousness of this endeavor. Initial commitments amounting to hundreds of millions of dollars have been publicly announced, with further rounds directed into materials research and laser technology. Collaborations span multiple countries, with laboratories across Europe, North America, and Asia contributing. While still far from the estimated multi-billion-dollar infrastructure needed for a full launch system, the point remains that hardware already exists, teams are active, and prototypes are being stress-tested. This is not a collection of speculative slides about future propulsion. It is an actual funded program where scientists report incremental successes and failures in real time. The mission timeline looks precise by comparison with other interstellar proposals. Once a launch array and sail designs are complete, the sequence would work as follows. Multiple gram-scale probes are attached to sails and lofted into near-Earth orbit or beyond. The laser system fires, applying many gigawatts of power for a duration of several minutes. That burst imparts gradual, controlled acceleration up to about 60,000 kilometers per second, 1/5 of light speed. The sail then detaches or folds, and the tiny probe coasts unpowered across the gulf between stars. In transit, it must endure interstellar dust impacts, cosmic rays, and deep space thermal gradients, all dangers for hardware at that scale. After roughly 20 years, the first probe would fly through the Proxima Centauri system, snapping images, measuring radiation and magnetic fields, and sampling the light reflected from Proxima B's atmosphere. The data would be compressed, encoded, and transmitted back toward Earth using a tiny onboard laser or phased radio system. That signal, limited by light speed, would reach us 4 years later. Altogether, the time between launch and receipt of the first scientific packet is about 24 years. The comparison with human lifetimes makes this powerful. A child alive today could still be in their 40s when the data arrive. That reality distinguishes Starshot from nearly every other interstellar concept. We are not talking about distant descendants or archivists millennia in the future. We are talking about results within the working lives of the people funding and designing the project right now. For the first time, the prospect of seeing an actual image of another star's planet's surface is described not as a dream centuries away, but as a plausible outcome of a single generation's work. Technical roadblocks remain, and proponents acknowledge them openly. Atmospheric turbulence on Earth will distort beams unless elaborate adaptive optics are used. The required laser system is vast in power, dwarfing anything built so far. Building and maintaining it requires consistent financial and political will for decades. Communication back to Earth from a chip-sized probe billions of kilometers away is not a solved problem, and shielding a gram-scale craft against grains of dust at relativistic speed challenges every materials model in current science. Yet unlike speculative warp drives or antimatter fantasies, none of these problems violate the laws of physics. They are problems of scale, cost, and resilience. While hard, they are mathematically solvable given enough investment and engineering persistence. It is this combination of ambition and realism that sets Breakthrough Starshot apart. The goals are audacious. They include constructing the largest laser system ever on Earth, designing sails thinner than any foil ever deployed, and transmitting data across light years with energy budgets measured in milliwatts. But all of it rests on principles already understood: photon pressure, reflective optics, precision lasers, and miniature electronics. In this sense, it marks a turning point in interstellar thinking. The distance gap remains enormous, but for once a direct engineering path has been drawn, and construction has already begun on pieces of it. For those who follow space exploration, this matters. It provides a line of sight to the first genuine interstellar data return within the century, and it organizes funding and scientific effort around a tangible milestone rather than vague speculation. Whether or not the full system completes as planned, the technologies pulled along, high-power lasers, lightweight nanomaterials, miniaturized sensors, will spill over into other fields of science and engineering. Breakthrough Starshot shows what happens when ambition targets the nearest star, not the nearest planet. It reframes interstellar travel away from dreamlike speculation and into a funded program of material tests and prototypes, quietly unfolding in laboratories right now. New theories in propulsion. When people hear that rockets and even fusion drives may one day take us to nearby stars, the next question often arises: what about the wilder ideas we see in science fiction? The thought of bending space rather than simply moving through it has long fascinated scientists and storytellers alike. Among the most famous of these speculative theories is the warp drive. It is not just a piece of creative writing. In the 1990s, a Mexican physicist, Miguel Alcubierre, wrote a mathematical description of what a warp bubble might look like in Einstein's general relativity. The idea sounds stunning in its simplicity. Instead of pushing a spacecraft faster through normal space, you manipulate spacetime itself. The region in front of the craft contracts, the space behind it expands, and the craft rides within a bubble where locally it does not move faster than light. The mathematics says such distortions are possible within relativity. That part is serious physics, but the details that emerge in the equations reveal why no one is preparing blueprints for warp engines today. The most intractable of those details involves energy. To compress and expand spacetime in the pattern Alcubierre described, you need a form of matter with negative energy density. This so-called exotic matter has never been shown to exist in the required quantities. Casimir effects in quantum physics show limited cases in laboratory conditions that mimic negative energy densities, but they involve tiny scales far smaller than any propulsion system would need. The kind of mass energy demanded by a warp bubble large enough to house even a small spacecraft is astronomical. Some calculations put it above the total mass energy of planets. In simple terms, the theory is consistent, but its ingredient list calls for materials that the universe may not actually provide in usable amounts. That is why the Alcubierre drive remains categorized as theoretical, not engineering ready. Still, the concept has not faded from physics. Researchers in 2025 continue to explore how modifications might lower the energy requirement. Some have tested variations of the warp bubble metric that would reduce the need for exotic matter from planet scale down to spacecraft scale, at least mathematically. Others study the limits of quantum field theory, asking if fluctuations of the vacuum might provide mechanisms to mimic negative mass behavior. These efforts do not bring warp ships closer to construction. What they do is sharpen our understanding of how relativity and quantum physics intersect. Every time someone refines the warp bubble equations, it helps map the boundaries of what Einstein's theory permits and where quantum fields could step in. For pure physics, that is valuable insight, even if it never translates into practical travel. Alongside warp discussions is another recurring idea: negative mass propulsion. Imagine a substance that, when pushed forward, accelerates backward. In Newtonian mechanics, this appears paradoxical, but in some formulations of general relativity, negative mass might exist as a mathematical solution. If paired with positive mass, the pair would in theory self-accelerate. This raises questions about whether such a system could be harnessed as propulsion without violating conservation laws. Negative mass has never been observed in nature, but every so often, laboratory experiments with exotic states of matter, such as Bose-Einstein condensates, produce effects that behave in ways that look mathematically similar to negative mass. Tiny clouds of atoms respond to applied forces with reversed acceleration. While this is not the same as literally finding negative matter, it keeps the door open for theorists to explore. It reminds physicists that what seems impossible sometimes deserves a second look at finer scales. Another thread of speculation focuses on manipulating spacetime through high-energy fields without exotic matter. If intense electromagnetic or gravitational fields could reshape spacetime curvature locally, spacecraft might slip between different metrics. In 2025, efforts in this direction remain deeply speculative, but some theorists publish models of how quantum vacuum energy could be engineered at high densities. The term metric engineering often appears in these discussions, an attempt to describe actively reshaping the geometry of space through technology. No experiment has shown spacetime manipulation on that scale. At most, early studies look at analog systems where sound waves or condensed matter mimic the equations of curved spacetime. These analogs allow controlled testing in the lab, though they apply only indirectly to propulsion. But for students of physics, they provide important experimental ground to think through how curvature and energy density interact. There is also the idea of wormholes, solutions to Einstein's equations where spacetime connects two distant points through a shorter path. Like the warp bubble, wormholes are mathematically consistent, yet they require exotic matter to remain stable. Without negative energy, the throat of a wormhole would collapse instantly. In the late 20th and early 21st century, papers outlining the stability problem for wormholes made it clear, without exotic matter, nothing lasting could form. By 2025, this has not changed. Wormholes remain interesting thought experiments that illuminate the boundaries of relativity, but they have no experimental reality. What all of these examples show is that physics allows highly imaginative pathways, but the gulf between imagination and hardware is immense. Chemical rockets may feel primitive compared to warp drives, but they launch real payloads. Fusion engines require decades of engineering, but they are rooted in proven laboratory reactions. Warp and wormhole concepts, by contrast, have no working components, no test hardware, and no obvious way to scale. That is not a criticism so much as a recognition of categories. There is practical propulsion, there is advanced but plausible propulsion, and then there is speculative propulsion. These categories should not be confused. They represent different parts of the spectrum: what we can build, what we are struggling to build, and what we may never build but still study because it teaches us about the underlying fabric of reality. In educational terms, these speculative paths serve an important function. They act as boundaries on our imagination. They remind us that the laws of physics leave room for possibilities far stranger than our current engines. They remind us, too, that mathematics and physics can describe things humans may never build. In that sense, these theories are not wasted effort. They extend the conversation about what interstellar travel might mean, but they also ground us. The absence of exotic matter is not a temporary inconvenience. It may be a permanent fact of physics. And if that is true, then warp drives and wormholes remain creative scaffolds rather than future blueprints. For anyone following interstellar studies in 2025, the message is becoming clear. Rockets will not take us to the stars. Fusion might. Solar sails may in some form. Antimatter sits on the far edge of possibility. Warp bubbles and wormholes. They remain elegant mathematics with unforgiving requirements. Physics does not bend simply because we wish it. That does not mean scientists stop exploring. It only means that our imagination and our laboratory work must be separated with care. For now, new theories in propulsion spark curiosity, generate debate, and tell us where the limits lie. But until negative mass is found or exotic matter created in usable amounts, the stars will not yield to shortcuts. They remain vast, and for the moment, physics holds us to the slower methods. Exoplanet hunting in 2025. Right now, one of the most dramatic shifts in astronomy is that we can no longer say Earth is the only confirmed world of its kind. The number of planets detected beyond our solar system has climbed steadily over the past 2 decades, and by 2025, astronomers have verified more than 5,000 of them. That figure alone is staggering because, for most of history, people assumed other systems might exist, but there was no direct evidence. Each new discovery adds one more piece to the picture that stars almost always have companions, and many of those companions are rocky, not just giant gas planets. What once felt like speculation has turned into a catalog that is growing faster than anyone expected just a decade ago. The technology that made these detections possible ranges from the transit method, where telescopes measure the subtle dimming of a star as a planet passes in front, to radial velocity surveys that detect a star wobbling as orbiting worlds tug at it. Missions like Kepler began this flood of data by monitoring hundreds of thousands of stars, and its successor surveys continued the work with even greater precision. Today, astronomers not only detect the presence of planets but can sometimes measure their size, orbital period, and equilibrium temperatures with remarkable accuracy. It changes the entire conversation. We no longer ask, "Are there other planets?" Instead, we now ask, "Which of them might resemble our own world?" The James Webb Space Telescope has deepened this transformation. Webb's infrared instruments have been directed toward exoplanetary systems, including those with rocky planets in habitable zones. It can measure the chemical fingerprints of light passing through a planet's atmosphere as it transits its star. In practice, these signatures might contain evidence of carbon dioxide, water vapor, methane, or other molecules we associate with habitability. The method does not offer images of alien landscapes, but it is the first step toward characterizing conditions on distant worlds where standing oceans and breathable atmospheres could exist. In 2025, Webb's data has already hinted at complex atmospheres, raising the possibility that some of these planets are more Earth-like than we dared hope when exoplanet studies began. This shift is crucial because it reframes our priorities for interstellar travel. The earliest discussions about reaching the stars imagined doing it for exploration's sake alone. The goal was simply to see what was there. With the growing catalog of exoplanets, the stakes are different. Missions are no longer targeting blank coordinates. They are aiming at specific destinations that may hold conditions suitable for life. This means interstellar propulsion research is not just about distance anymore. It is being guided by the knowledge that there may be worthwhile targets. That change in perspective is why many in the scientific community compare today's moment to the age when maps of Earth's continents first took form. Only now, the maps are of suns and orbiting rocky bodies, each star system presenting new reasons for us to find a way across the gulfs. Among these systems, Proxima Centauri remains the most talked about. It is the closest star to our own, a red dwarf just over 4 light-years away, and it has at least one known planet in the zone where liquid water could exist. Proxima b is only slightly more massive than Earth, and it orbits its parent star at a fraction of the distance Earth sits from the Sun. That closeness is necessary because red dwarfs emit far less light and heat. But being in that location also means the planet faces challenges. Stellar flares could strip away its atmosphere, and tidal locking might keep one side in perpetual daylight. Webb and other instruments are examining these conditions carefully, and even if Proxima b turns out to be hostile, the fact remains. There is an actual world within reachable distance of light-speed technology, not just a theoretical dot on a chart. For interstellar planning, that puts Proxima Centauri at the top of the list. Another system that holds remarkable attention is TRAPPIST-1, located about 40 light-years away. While far more distant, it is extraordinary because it contains 7 rocky planets all orbiting a small star. Of those, at least 3 lie within the habitable zone where liquid water might persist on their surfaces. What makes TRAPPIST-1 especially valuable to astronomy is that its planets, being close to their dwarf star, transit frequently, giving telescopes repeated chances to study their atmospheric light signatures. Already, these studies suggest that some may have thin atmospheres, while others may retain more robust envelopes of gases. With each update, they become stronger candidates for long-term study, especially because a single mission could, in theory, visit multiple habitable zone worlds in one system. That detail makes TRAPPIST-1 not just a collection of data points, but a miniature planetary laboratory awaiting exploration. The range of candidates continues to expand beyond these famous names. Systems like LHS 1140 and Kepler have planets that fall into categories we call super-Earths, larger than our planet but still rocky and potentially stable for atmospheres. Some even orbit stars more sun-like than Proxima or TRAPPIST-1, creating environments closer to what we experience on Earth. The sheer diversity is striking. There are planets with years lasting only days, others completing orbits in over 1,000 days. Some worlds receive starlight brighter than we ever experience here, and some linger in dim twilight. This variety is directly relevant to interstellar travel because it means we will have genuine choices about what kind of world to investigate first. As the catalog of exoplanets grows, the challenge becomes not just finding them, but prioritizing which ones matter most for future missions. That prioritization now involves careful checks. Is the planet in the habitable zone? Do current telescopes suggest a stable atmosphere? Does it orbit a quiet or an active star? And how reachable is it on the scale of interstellar distances? These questions are not academic. They form roadmaps for potential first targets. Breakthrough initiatives like Starshot already frame their mission goal not as reaching another star in the abstract, but as reaching Proxima Centauri to look at Proxima b. That narrowing of focus is what makes our current time unique. Targets exist with coordinates, with known orbits, and with measurable atmospheres. The presence of so many confirmed worlds also alters public imagination. For younger generations seeing astronomy headlines, planets do not appear as rare jewels but as common parts of the galaxy. 5,000 confirmed and many more unconfirmed paint a sky overflowing with potential. Each faint point above Earth could be the center of its own neighborhood of planets, some frozen, some seared, and some balanced in ways that might support rivers, weather systems, and possibly even life. This isn't abstract speculation anymore. It's a growing body of empirical data, cross-checked across telescopes and surveys. Every year adds new confirmations, each number tightening the sense that our galaxy is alive with real destinations to fly toward. And this has a practical consequence for propulsion studies. Engineers working on concepts like solar sails, fusion drives, or antimatter don't just talk about speed in isolation. They now anchor their estimates with questions like, how many years until we can image Proxima b's atmosphere up close? How quickly could a probe traverse the TRAPPIST-1 system? The data aligns propulsion goals with astronomical discovery. The journey can now be matched to a clearly defined endpoint, tailored to systems visible through Webb. In conversations about funding and public support, this connection may prove decisive. It is far easier to secure long-term investment when the target is not anonymous but bears a name, a mass estimate, and atmospheric detections recorded from telescopes already in operation. By 2025, this is the state we stand in. The list of distant worlds is not hypothetical. It is more than 5,000 entries long, expanding with each new observing season. Some of those entries fall into categories that excite biologists as much as physicists, planets that might sustain chemistry similar to Earth's. That growing confidence reframes interstellar travel from vague speculation into purposeful direction. The starry sky is no longer a backdrop of abstract light. It is filled with specific destinations, planets with orbits and compositions we can measure, worlds that, for the first time in human history, feel like places, not just points of light. Costs, collaboration, and timelines. For all the creativity poured into new propulsion concepts, there is another question that always looms just at the edge of the discussion. Even if a design works, who is going to pay for it? Ideas for reaching other stars are compelling, but they come attached to costs that run far beyond a single agency's yearly budget. They are not weekend experiments or small-scale probes launched on spare funding. They require infrastructure, decades of development, and man-hours large enough to stretch across generations. This financial reality is not exciting to talk about, but it is unavoidable. Every roadmap toward interstellar travel eventually reaches the same obstacle. The brilliance of the technology matters little if no one can sustain the bill. Take breakthrough Starshot as the closest real-world example. Its vision is crisp. Build an array of ground-based lasers powerful enough to accelerate gram-scale probes to a fraction of light speed. The materials and technology overseeing its sales are already under investigation, but the price tag for the array itself is staggering. Estimates published during its early proposal years already place the cost in the billions, likely pushing toward $10 billion or more depending on how large the system scales. This doesn't count the iterative costs of design, testing, and prototyping over the decades required before the array even functions. Even with wealthy private backers, the sheer scope of that infrastructure surpasses what a handful of philanthropists can absorb. The project requires shared financing on a global scale. Fusion propulsion studies have their own budgets building beneath them. Governments and international consortia fund experimental reactors, mostly aimed at producing clean energy for use on Earth. Facilities such as ITER consume tens of billions of dollars already, with the expectation that over time these investments will lead to practical power stations. For propulsion specialists, the advantage is that progress in energy generation can double as progress for space. Reactors that succeed commercially provide the foundation for scaled-down versions in spacecraft. Yet the kind of compact drive needed to accelerate star probes would require separate design teams, funding, and testing protocols. Even optimistic timelines list costs ranging from hundreds of millions into multi-billion ranges for each demonstration stage. This is far outside the budget of isolated research labs. Solar sailing, while often imagined as a cheaper alternative because it requires no onboard propellant, is not without its own high price tags. A sail stretched across a single kilometer, made with ultra-thin reflective material, runs into deployment challenges that cannot be solved with CubeSat budgets. The labor, testing, and complexity of deploying sheets so delicate require entire mission budgets in their own right. Add the idea of coupling sails to beamed propulsion, lasers or microwaves, and the cost immediately rises. Powering an array capable of transmitting light across astronomical distances requires industrial-scale investment. Estimates range again into the tens of billions when scaling above prototype sizes. These are sums impossible for single institutions to cover. Because of these figures, the pattern emerging in 2025 is clear. Every practical conversation about Starflight draws in multiple kinds of partners. National space agencies remain at the center. NASA, ESA, and JAXA all direct funds towards solar sail demonstrations and propose fusion studies. Smaller nations often join through university-side collaborations, contributing engineering or component-level design work. Around these agencies orbit private ventures. In the United States, small aerospace companies participate in contracts for lightweight composites, deployment mechanisms, and high-efficiency electronics. In Europe and Asia, universities form the backbone of new algorithms for navigation and data transmission. Then there are the billionaires and private foundations. Their role has been to seed daring concepts, covering risky material research that government budgets shy away from. Across these different players, no one institution is carrying the field. This distributed funding also opens another important issue. Interstellar projects span decades, sometimes centuries, and funding cycles in governments rarely extend beyond 5 to 10 years. If a parliament or Congress changes, budgets can vanish overnight. That level of uncertainty is already familiar in the smaller context of planetary science, where missions often live and die based on shifting political winds. For Starflight proposals with timescales longer than human careers, such inconsistency is fatal. Analysts in 2025 stress that international frameworks may need to mirror those in fields like climate science or particle physics, where large-scale commitments bind multiple nations into agreements spanning decades. Without this scaffolding, interstellar projects will begin only to fade as political focus drifts. Timelines offer their own sobering perspective. Robotic missions have a plausible route inside this century. Breakthrough Starshot's target places flight time at 2 decades, with another 4 years for a signal to return. That is tangible within the scope of current generations. Fusion-powered probes, if demonstration reactors mature in the 2030s and 2040s, might see test platforms by the 2050s or 2060s. Such craft could begin experiments in near-solar travel, eventually building confidence for interstellar missions launched near century's end. Solar cruiser demonstrations are already on schedule for this decade, pointing toward larger sails in the 2030s. If each test succeeds, a sail probe to the outer solar system could leave before mid-century. These robotic paths are the meaningful milestones before anyone imagines human passengers. For crewed journeys, the timescale stretches far beyond our immediate horizons. The life support requirements, radiation shielding, and energy demands to sustain people on decades to centuries-long trips move the complexity into another category. Even optimists in 2025 admit that human voyages beyond the solar system are not matters for this century. They land centuries ahead, requiring technology leaps we cannot forecast. This does not make robotic exploration less significant. If our first probes bring atmospheric spectra or images from another star's world, it may inspire the same cultural impact as seeing Earthrise from Apollo 8. Those missions alone can reshape how humanity perceives its place in the galaxy. In terms of global responsibility, the narrative that interstellar travel is a shared effort has become stronger with every passing year. The costs exceed military budgets of most nations. The scientific and material expertise spans continents. Even breakthroughs in storage materials come from collaborations that cross borders. Unlike planetary missions that one nation may launch proudly under its own banner, a star probe cannot arise from nationalism alone. It will require pooled budgets, shared risks, and joint scientific returns. The model resembles how humanity built the International Space Station or partnered on CERN's Large Hadron Collider. Distributed costs balanced against distributed benefits. Some may see this complexity as discouraging, but the opposite interpretation is just as valid. When the scope of a project towers this high, it gathers not only engineers and physicists, but a broad coalition of politics, culture, and public imagination. The sums required to assemble ground-based lasers or orbital reactors are immense, but so too were the sums for Apollo in its time. This does not minimize the challenge of spending billions across decades, but it contextualizes it. Human societies have managed cooperative projects of this order in the past. What changes here is that the outcome is not satellite television or lunar landings. It is the first step toward expanding beyond our solar system. By 2025, the conversation is no longer only about propulsion physics or sail materials. It is about governance, finance, and how societies prioritize collective goals that offer no immediate return. Interstellar programs face the same obstacle as any megaproject in history, sustaining vision across many political cycles. They survive only when they are seen as more than science, when they become cultural priorities tied to human identity. The question is not simply whether lasers can push a gram of silicon across interstellar space. It is whether different nations and institutions can sustain a 100-year commitment to see it through. That is what clarifies the reality of Starflight. It is not a solo pursuit but a collective moonshot, requiring as much shared willpower as shared physics. Interstellar travel is no longer just a poetic dream. Step by step, the conversation has shifted into roadmaps, hardware tests, and designs that now live in laboratories rather than novels. The distances remain unforgiving, but the ideas of sails, fusion, and directed beams have given us outlines that engineers can realistically pursue within this century. It's worth remembering that the first Starship humanity builds may already exist as sketches or prototypes on someone's desk. The question is not if, but when. So imagine, which of these distant worlds should we send it to first? And would you choose to ride aboard?